Hi there, my name's Lauren Madigan. I completed the HSC in 2012 and received an ATAR of 99.65 as well as first in the state in HSC mathematics. I'm here to help you try and get a better understanding of some of the main concepts that may present as difficult throughout the year. Today we're going to take a quick look at the basic algebra and arithmetic and then move on and focus on plane and coordinate geometry. And the first thing I'm going to have a look at may seem intuitive to many of you, but what's really important is being able to recognize it in the context of a harder question. So here's a look at some basic formulas that you may have been familiar with since the start of Year 11 and even earlier. Like I said, while many of them look familiar, what's really important is being able to recognize them in a harder exam question, as you'll be amazed how many times simplifying something as basic as this can lead you closer to the answer. Looking down especially at those here in green, you can see a quick way to remember them is known as SOAP. So here, looking at the case of x cubed minus y cubed, we've got a negative sign. So then we've got the same sign, the opposite sign, and an always positive sign. So that's mirrored by your SOAP. Here, just to confirm that, we've got a positive sign. So same, opposite, always positive. So like I said, just keep these in the back of your mind throughout your HSC course, and you never know when they may come into handy. So now I'm going to move on to some line and plane geometry. The first thing we're going to look at is some basic properties of lines, and again, while many of these may seem obvious, what's really important is being able to recognize them in a much more complicated question, as it'll help you simplify the answer and get much closer to that result. So vertically opposite angles, we know that these are always equal, whether the lines, no matter what angle those lines are intersecting in, the angles here represented by x, these will always be equal. But once we go to parallel lines, we get a few special rules. So the first of these is that on parallel lines, alternate angles will always be equal. That's represented by the green x's and the yellow y's to the right. Also on parallel lines, your corresponding angles will also be equal. Again, this is clearly shown on the diagram, provided as long as those orange lines are parallel, the 110 degrees will be equal in both of those spots. Another thing that can come quite in handy is that your co-interior angles are supplementary on parallel lines. And this means that they add to 180 degrees, and they're shown there by the two yellow lines. Now, what if we were asked to prove that two lines were parallel? Well, this easily follows from what we just discussed. So all we need to do is to show that either the alternate or corresponding angles are equal, or the co-interior angles are supplementary. Another thing to keep in the back of your mind when you're working through these kind of geometry problems is that if two lines are both parallel to a third line, then the three lines must be parallel to each other. You may see this pop up in examples from time to time. Now we'll go have a look at some types of triangles. While this probably isn't the most common thing to be asked directly in a HSC question, again, knowing it can only help you in the context of a more complex question. So the first type of triangle I'll look at is the scalene triangle. This has no two sides or angles that are equal. Then we've got a right-angled triangle. This contains one 90-degree angle, and the longest side is referred to as the hypotenuse, denoted here by C. An isosceles triangle has two equal sides, and hence its base angles will always be equal, as shown in red. Then, an equilateral triangle, as you're probably familiar, has three equal sides and three equal angles, while an acute angle has all of its angles acute, and an obtuse angle is a triangle that contains one obtuse angle. Another rule to keep in the back of your mind as you're working through these questions is that any line joining the midpoint of two sides of a triangle, say from this point here to this point here, is not only parallel to the third side, but also exactly half its length. That can be quite helpful when trying to prove many things. Quick look at congruency and similarity. So we've got 4 tests for congruency. The first of those is 3 equal sides, so it's referred to as SSS, and obviously if 3 of the sides are equal, then your triangles are exactly congruent. We can also have two equal sides as long as their included angle is also equal. We can have two angles the same and one side equal. Now that does not matter which side it is in relation to the two angles. And we can also have a right angle in each triangle, an equal hypotenuse, and as well as one additional side angle. All of those should give you complete proof that you've got a congruent triangle. Now looking at similarity, we've got three proofs that we can use to show that a triangle is similar. So we can say that the three pairs of angles are equal. Now this does not mean that it's congruent. We have to be careful here because the sides may be in proportion with equal angles, but not necessarily exactly the same. Saying that, three sides in proportion is your second test for similarity. The third test is that two sides are in proportion and the included angle is equal. And this is shown here, that while those angles are all the same, your triangles are not necessarily congruent. Another thing that pops up in geometry is the ratio of intercepts. So when two or more transversals cut the parallel lines, the ratio of the intercepts will also be equal. So here we've got our ratio of PQ to QR is going to be exactly the same as JK to KL. Another thing to keep in mind. Quick recap of some angle sums. Again, many of these you may be familiar with, but if there's something you haven't covered, you may want to jot it down. So the interior angle sum of a triangle, probably where is 180 degrees. Any quadrilateral will be 360 degrees. And the exterior angles for any polygon will be 360 degrees, where a polygon is any n-sided figure, where n is just an integer. The interior angles of a polygon in general will be 180 times n minus 360 degrees, where n is the number of sides. And we know that the exterior angle of a triangle is equal to the sum of the opposite interior angles. Now we're going to look at a few shapes specifically and the proofs that can be used to identify these kind of shapes. Now that does quite often come up in a question, and it's very important to be familiar with these. So the first of these shapes we're going to look at is the parallelogram. So this is a quadrilateral that has opposite sides parallel. There are several properties of a parallelogram that are essential to know in order to prove that something is in fact a parallelogram and allow you to use these properties to solve the next parts of the questions. So we'll have opposite sides equal, opposite angles equal, the diagonals will bisect each other, and also bisect the parallelogram into two congruent triangles. So how do we prove that something is a parallelogram if we were asked to? It can have two pairs of opposite sides equal, two pairs of opposite angles, one pair of opposite sides both equal and parallel, or if the diagonals bisect each other. Now we'll look at a rectangle. So these shapes can quickly build on from one another, mostly falling back to that parallelogram. So a rectangle can be thought of in terms of a parallelogram with one angle, a right angle. So its properties include all of those of the parallelogram, and in addition, its diagonals are equal. So how to prove this? If the diagonals are equal, then it's a rectangle. Now we're going to move on to a rhombus, and again we're going to take this back to the parallelogram. So a rhombus can be thought of in terms of a parallelogram with two adjacent sides equal. Again, the properties include all of those of a parallelogram, plus some additional things. So the diagonals will bisect each other at right angles, as shown in the diagram, and the diagonals also bisect the angles of the rhombus. Very important facts to keep in mind. To prove that something is a rhombus, there's many ways we can do it, and this is actually quite a common exam question, and they will sometimes only give you enough information to do it one of the three ways. So I would highly recommend being familiar with these methods. So we can show that all four sides are equal, that the diagonals bisect at right angles, or that one pair of opposite sides are equal and parallel, and that adjacent sides are equal. So this third proof follows straight from the definition of a rhombus from the parallelogram. Helpful to keep in mind. Moving on to the square. The square comes from a rectangle, and that's a rectangle with a pair of adjacent sides equal. Its properties are all of those of the rectangle, as well as its diagonals are perpendicular, and the diagonals make angles of 45 degrees with the side. Some quick miscellaneous shapes before we move on. Trapezium has one pair of parallel sides. A kite has two pairs of adjacent sides equal. Now again, many of these previous notes may have seemed quite obvious or basic compared to some of the topics you're doing now, but like I've said many times already, we really need to be quick on being able to recognize these things in a harder question, but we'll do an example at the end. So some quick area formulas that you should be familiar with, and again, many of these may not be provided when you need it most, so good to just keep them in mind. Your square is simply the length of one of the sides multiplied by itself. Your rectangle is your width times your breadth. Triangle, half base times your height. Circle is pi r squared. A trapezium is half your height plus the sum of your sides, and a rhombus or cut is half xy, and that's where x and y are your diagonals. And your parallelogram is simply your base times your height, or your two sides times the angle between them. Some quick volumes to know. These are presented here for the sphere, and we've also got the surface area. Then for the cylinder, now be careful with the surface area of the cylinder. If your cylinder has no lid or base, then we won't include the 2 pi r squared. Similarly with the cone, if your cone does not have a lid, then your surface area will only be the pi rl, where L is the slant height. If your cone does in fact have a lid, we'll need to add the pi r squared to this formula. Now we're going to move on to line and coordinate geometry. It's very similar in the types of skills that have to be applied, and the topics are often covered around the same time, so hopefully this will follow on nicely. So two very important